Hello. In this video, I'm trying to give you a overview of reliability engineering and aspects of the reliability engineering in the past and present. The outline of this presentation would involve that first addressing the question of what is reliability engineering, and it follows with discussions on the areas of research in reliability engineering and reliability engineering education. Reliability engineering overview. What is reliability engineering? Reliability engineering measures and improves resistance to failure over time. It estimates expended life and predicts time to failure. I would hope that this particular definition would actually becomes more crystallized as I go through this presentation. So what do reliability engineers do when actually doing this kind of engineering analysis? They study ways to prevent failures from occurring, and this means that they design items robust enough that failures don't occur, or at least occur in a very minimum number of times. And they would, once those items are being put into operation, you monitor and also correct any degradation and damage which is avoided, which is observed to avoid any future failures. Reliability engineers develop and use models to assess damage, degradation, and aging of items. When I'm talking about items, I mean a very broad definition of things such as hardware, software, human, structures, components, systems of systems. And so by item, I'm using the word as it's a very general definition of things that reliability engineering applies to. Reliability engineers also predict the time of failures. That is, when a component or an item which is operating, we would expect to see a failure. When do we see? Of course, this is a prediction of the future, involves uncertainty, and that has to be factored into the assessments that reliability engineers do. They also apply failure prevention and prediction methods to hardware parts, components, structures, systems of systems, human actions, and software products, the collection of which I define as items. And finally, they develop prognosis and health assessment methods of items which are actually in operation or being designed. I'm going to talk a little bit about the evolution of reliability engineering over time and tell you where it came from. There are essentially in this evolution, you could observe two different overlapping themes for modeling life and performance of items. And these two involves, the first one, which is older one, involves data and evidence-driven views. This methodology is based on collecting data and assessing future occurrences or behavior of items based on the past occurrences of failures or past occurrent data regarding the performance of these items. So clearly it relies on statistical and probabilistic methods to make that kind of an estimation. It also has the next theme that has emerged after this first theme is the physics-driven theme. This view is essentially comes up with an empirical representation of the physics of how things degrade and fail. And to establish that, of course, requires a significant amount of knowledge and testing and understanding of the underlying behaviors of failure. Aside from the empirical approaches, there are also physical laws that one can more recently have been used that you could apply to come up with these physics-based thinking of how components degrade and fail. I'm going to talk a little bit about both of these kind of techniques. Examples of areas of applications of reliability engineering is very broad. Reliability engineering is a systems approach, and it spans over a very wide area of applications. So it applies in design, for instance, in assuring reliability, in testing, in safety and assessment, in human, software, and machine interactions, and on developing and establishing warranty for products. So especially on the human, software, and machine, more recently these systems are becoming more prevalent in use, and we see often that failures that we observe from these kinds of systems involves the interactions between these elements of human interacting with software or software interacting with machines or vice versa. And these are the failures are typically, each of these elements are by themselves are reasonably reliable, but the interactions between them could cause faults and failures. The next area of example of operation is of applications is in operations, during operations of these items. These involve establishing repair, ideas of how to do repair, how to maintain these components, risks imposed by these components, and by risk I mean that if they do fail, there are often consequences in terms of either human consequences, health consequences, safety, environmental effects, or simply economic consequences. These are what we call risks of failures, essentially. Other applications in operations involve obsolescence. Typically, very complex systems, again, are important to know when they are actually reaching a point that they are no longer should be used or unsafe to use, and that's the point that obsolescence becomes important. Again, reliability engineers actually play a big role of understanding how to deal with these obsolescence questions. And finally, when a failure does occur, one of the aspects of important work of a reliability engineer is to find out what are the root causes of those failures. Let's move on and discuss a little bit the data on evidence-driven view, which was the first view which I described, aside from the following view that came, which was physics view. In the data and evidence-based view of reliability actually was the beginning of the reliability engineering as a formal discipline. It came in the post-World War II initiative as a post-World War II initiatives, and that came because we saw a lot of unreliability, especially in the electronics, and fatigue of structures and components that were in the war zones, and that came actually because of that, and originated and inspired by weakest link model, which was in existence at that time, statistical process control, insurance assessments, and finally demographic and mortality analysis methods. These were all in use at that time, pre-World War II. So it benefited from methodologies that were developed under those fields and defined reliability of a basic item based on the reliability of the data or past historical data that were collected. And the objective of it was to find the likelihood of a no failure or success of equipment based on these data observation by coming up with a probability distribution function of f of x given some parameters theta, developing where this distribution described the time of failures, of course, again, based on the past or historical occurrences of those failures, these distributions were developed. Very formally, reliability engineering defines a measure of reliability as the probability of a time to failure, which is now considered as a random variable, to exceed a desired time of failure that we'd like to have. So as long as that failure occurs beyond the time of desired lifetime of the component, that could, for instance, be the mission time of a given element, or it could be the lifetime desired for a given item. As long as the time of failure exceeds that time, then the component is considered probabilistically reliable. And of course, if you have the probability density function or distribution of the time of failure f of x, if you integrate this from of this time or desired time t to a time infinity in the future, then that gives us the reliability as you see from this equation. So reliability, once you have the reliability of items for which we have the data, if you are going and actually find the reliability of the system now, which would be a collection of different items, these items, so typically very complex systems are very reliable, and oftentimes we don't have enough data for them because they don't fail that often. But their constituents, their basic components do fail, and we do have more data on them based on which we could actually use the equation which I just described to find the reliability of them. So therefore, reliability of these highly reliable system is found from an equation which relates reliability of the system to the reliability of these items that constitutes those systems. So that equation you see is reliability of system equal a function of reliability of I, is a function that we try to find in reliability engineering. One of the basic methods which are used is reliability block diagram, and the second method, which is more in use and much more powerful, are the logic-based systems which we use to find these relationships. For example, fault tree analysis or success tree analysis, these are the logic-based models that actually make or try to find these kinds of relationships. Typically, the based assumptions that we make in reliability engineering involves some fundamental and very important aspects in these data-driven methods. One is that, first of all, historical data are the truth about the failure, and that they would repeat themselves into future. That is, whatever we saw in the past would repeat in the future. Of course, this is a major assumption, and often though it is a good assumption, sometimes it actually causes a underestimation of reliability or overestimation of reliability, and that is a very, very important aspect that causes this view of data-driven view or evidence view actually flawed in certain cases. Therefore, based on these methods, of course, we also, another aspect is that the maintenance and repair that we do during the lifetime of the component renew the item into an improvement in its reliability, and that's another assumption that we make. Finally, we measure in this particular case degradation not based on physics of the degradation, but rather a probabilistic term, which we call cumulative hazard. So in this equation that you see right here, this equation describes the reliability as the exponential of the negative of what we call as the cumulative hazard. And that the cumulative hazard is the integration of what we call a hazard rate, where the hazard rate is essentially the probability of failure over a period of time divided by that time. In other words, instantaneous rate of occurrence of failure or failure rate in this case. So hazard rate is then defined in reliability as the probability distribution function of time of failure divided by the reliability, both of which I defined in my original equation right here. So, so given all of that, I like to now say that the fact was that certain cases, the data-driven, as I noted earlier, had some flaws in it because the field data did not really supported or corresponded to the estimates of the reliability prediction ahead of time. And that is because not all the historical data would be related, because a component may be working in a completely different environment, and a new component which is operated in a new environment may actually experience totally different behavior of reliability. And for that very reason, physics-based view of reliability came based on several reasons. This view came in the 1960s originally with a number of U.S. Department of Defense support, and then it kind of stopped for a while until the 1990s, where it was revived again. The approach that this methodology takes is that it says that the failures occur because of some underlying phenomena which we call failure mechanisms. These failure mechanisms are things that causes the failure or degrade the component, such as corrosion, such as fatigue of the equipment or materials, such as cracking, stress corrosion cracking. These are the failure mechanisms that ultimately accumulate damage, and once the damage is accumulated to the point that the component can no longer endure that damage, or in other words, we reach the resistance to damage, then it assumes that the item fails. It's actually a much more profound, much more specific definition of reliability in this case. And also, aside from damage, you could think that that these failure mechanisms could also cause the performance of items also degrade. Performance could be, for instance, resistivity of a resistor could increase as it's exposed to higher temperature, or efficiency of a pump could degrade to a point that no longer actually is efficient enough, or a compressor in the same manner. These are declines in performance that could also be caused by these underlying failure mechanisms. So physics view tries to model these mechanisms specifically, and what it finds, the approach besides these physical model is essentially to come up with also a second case, is that certain components also do not necessarily experience degradation of any sort, either in performance or in damage. Rather, there are impacts or certain causes that a stress may be existing that exceeds the strength or capacity of the item to resist. These are the components that not necessarily degrade, and for example, these could be loadings that could take a component only into its elastic region. These are cases where you only, after removal of the load, you go back again to the same condition as it was. Only a failure occurs when this load exceeds the strength of that item, and a failure occurs. These are the models of the physics that often is used in reliability engineering, is the physics-based view. And so in the physics-based view, the physics of failure tries to develop a model from which you could derive essentially the time to failure empirically. And so it tries to establish the time of failure, T of the time of failure, as a function of all the loads or other factors that affect this degradation or reduction of the performance. These could be these items that, for instance, you see here. And in this particular equation, S sub O is the operational stresses, and S sub E are environmental stresses that apply on the component. G could be geometric related factors. A smaller component, for instance, could behave, a smaller pump could behave differently as compared to a larger pump of exactly the same design. A bunch of parameters could also exist in this model, and finally there could be some initial flaws or defects in the system that we don't really have to consider in our physics model. This is the establishment of these physics model. They need to be done, of course, for every failure mechanism separately, and a model like that needs to be developed. These kinds of technique was inspired originally from fracture mechanics, and the way we develop them most often relies on the concept of accelerated life or degradation testing, whereby we fail components by accelerating or applying these stresses that you see here at a much higher rate than normally operated in use, and causing them to fail, and then in a faster time, so we can gather some data based on which we could use and develop empirically these models by using some kind of a regression analysis or more advanced regression analysis, Bayesian regression type. And finally, these are the models that become then the models that represents the time of failure. Typically, because of the fact that we won't have a lot of data, even in these cases, these models are also involve some uncertainties, particularly the parameters that are here could be having uncertainties with that. So generally, these models are more appropriate to be called probabilistic models of physics or probabilistic physics of failure models. And we use them for simulation or application. The benefit of these models is that, of course, there are very dependence in this case in historical failure data which have been gathered from different conditions and different operating fields, from different stress conditions and all that. And therefore, it could be much more specific to the stresses that the particular component sees or geometry of that particular component. It easily is connected to the physics, and it's more accepted by technical people. It addresses the underlying causes of failure. As I said, these causes where I define them as failure mechanisms, and each would be specific to a specific item. So if an item, or let's say an automobile, operates in a given condition, in a given environment, in a given place, which is dry, for instance, as compared to a place which is very humid and corrosive environment, then of course the two would behave differently. These models allow you to properly find and estimate the reliability of these kinds of items. The drawback, on the other hand, is that, of course, as you could note here, that is harder to model, and you need to develop a model like this for every failure mechanism. And when we develop these models, we are looking for markers of failure, not specifically the damage, which could be larger than the markers of damage. So marker of damage could be, for instance, the size of the corrosion, could be the depth of the corrosion, could be amount of wear that is released into to the outside. It could be the size of a crack initiated due to fatigue. All of these are markers of damage. But when a fatigue is generated, there could be also damages or micro cracks that are not necessarily visible. And therefore, the model that is applied here is actually only models the big items which were measurable, these so-called markers of damage. And that's actually a sort of a drawback of using that, as the fact that not every damage is modeled in this case. And of course, it's based on small experimental evidences because it's very expensive to run a lot of experiments to develop these physics-based models. And so for that reason, these parameters of the model could involve some uncertainties. Examples of current area of research in reliability engineering on the data side base view, there are significant advances have been and has been going at this time in the past and is going on right now in the area of application of advanced Bayesian models and data analysis and data validation. Bayesian techniques allows you to bring smaller amount of data, but some prior evidences and prior data or expert judgment into analysis or data from similar components and bring them all together. Experiences of, let's say, an organization could be brought into a new product which is being developed. These are very powerful technique and has a lot of promise and has reduced this issue that I was talking about, the relevance of historical data into applications of the future, using of the models for future estimation of the components. It's been used, another area of application has been developing warranty, especially for product and evaluation. Reliability growth has been a very big area of research and use in reliability engineering. This is when we develop a product and we want to make sure that we reach a given level of reliability desired by the buyer or by the developer of the product. Other areas of major research are generalized renewal process. These are cases where we renew during the repair or maintenance a given component, and so these modeling methods allows you to factor into the component to how well, or to the item, how well we can actually renew them from complete and perfect renewal all the way to minimum renewal can be modeled by these techniques. Quite a bit of advances has been made, and still a lot of activities are going on in this area. Software reliability is also another area of major research. Software is making more and more, becoming a bigger and bigger part of a complex system and component of a complex system, and of course their interactions with system, as I noted earlier, is becoming much more important. Software reliability has been a major focus in reliability engineering in the past. Another very important area is human reliability, and we have made quite a bit of advances. There's still a lot of advances to be made. These are the cases where a human can miss a given action that he or she was supposed to do during the operation of a component or use of a given element or during operations. This could be in hospitals, it could be in operation of aircraft, it could be in the operation of nuclear power plants. All of these, human reliability has become a very major and important issue. And finally, another area of very importance in the data analysis, in the data area, is the data science. We are relying more on prognosis and health management, and we are gathering quite a bit of information from sensors and using those data in predicting reliability. And sensors typically bring large data, big data into the scene, and then we have to deal with these data and factor them into an estimation of reliability. So data science has become a very important and significant area of establishment and research in reliability engineering. Other area are information fusion. Completely significant amount of information could be gathered from different sources of very diverse nature, and they need to be brought in and combined. Methods of simulation tools such as Markov chain Monte Carlo simulation, MCMC, recursive Bayes methods, Bayesian filtering. These are techniques, again, in data science which are very highly used. And finally, pattern recognition that describes patterns of certain degradation or certain failures, clustering of the data and classification of data to only find the data which are most relevant to a given situation and reduce the historical data to the most relevant have been also an area of major research. In the area of physics-based review, the most important advances have been made in hybrid models. By hybrid models, I mean different types of models that have been used traditionally in reliability engineering, such as fault-tree analysis, such as logic-based models, in this case, and computational algorithm, which are numerical. How you can maximize the use of these techniques together and work them harmoniously together to estimate reliability. Another area of quite a bit of advance has been, and research has been focusing on Bayesian belief network, where we are trying to actually learn from the data and estimate reliability given situations that occur, how you can estimate reliability conditionally upon events that we could observe. Another aspect is the dynamic belief networks, another very highly focused and advanced area of research these days. How can we use, again, information and data from degradation from information which are gathered dynamically and then find the reliability conditioned on those information. Other areas is, again, borrowed from artificial intelligence and computation is agent-based computation and modeling has been used in reliability engineering for systems analysis and fusion of data, large data, and also use of these failure mechanisms or physics of failure model and treat them as agents of failure. Also, this concept is used in modeling human errors and human actions, again, as agents of failure. And this has been, again, another area of good research and expansion these days. Neural network applications, again, in machine learning has been used in physics-based models to develop and learn from degradations that are observed or tested to learn and train different networks for future applications. Another area of expansion has been in probabilistic physics of failure, especially in accelerated life and degradation testing. Different methods of testing has been used. Time varying, for instance, tests have been one area of expansion, especially these areas when combined with Bayesian model and technique have been a very good area for research and development. Finally, prognosis and health management has been a past 5-6 years have shown a major rise in applications in reliability engineering. The concept is to find the reliability of the systems and measure and support the resilience of items, when to replace them as information is gathered during the operation of the item, and finally also manage the repair and maintenance using sensors, again, large data, and these are areas of research, again, in the prognosis and health management. Another area is the reliability of autonomous systems, especially these could be the robots, could be driverless cars, especially also very complex cyber physical systems, safety and security, especially when it comes to do with infrastructure system, complex systems of systems, areas of, again, quite a bit of research going on. Another area of research has been fundamental. I mentioned it earlier in my talk about the research on the fundamental science of reliability engineering. This is to go away from the pitfalls of empirical modeling, because as I noted, in reliability we are just measuring in these empirical methods the markers of damage, but damage is bigger than those markers of damage that we see. The damage itself is larger than that. So thermodynamic has been one area of use, especially the second law of thermodynamics information theory, and statistical mechanics are three areas of quite a bit of advance. I will again talk a little bit about this. So to summarize the reliability, originally we tried to find this historical data to find this distribution of the time of failures. We went to historical data to find these times, and then fit a distribution to those times, and then use this distribution for future. Later on, we came and developed the physics of failure, finding some initial damage, and growing that damage based on these physics models to find how the damage is accumulated for each of the failure mechanism, and instead finding these times of failure based on these physics models, until this damage reaches a given endurance or capacity of the system to fail. And of course, even this capacity is measured by testing. So once these are used, and as the test going on, this amount of damage is found. Each of these paths shows the path of damage due to different tests that we carry, and therefore at each time we find a distribution of time of damage. Even the amount of endurance could be distributed, as I showed here. So in summary, reliability engineering entered three different phases, still all these three exist. One is the data-driven technique, more advances. We use historical data to find the time of failure. The second method was empirical method. We use failure mechanisms of different sort. We go into developing a model and fit a model of how these would accumulate damage. And then we use a model which says that once that damage exceeds an endurance or capacity of the system to stand that damage, or that item to stand the damage, then a failure occurs. So the idea is to come up with a physical model, which I showed you earlier, to find these kinds of traces. So if you are having a given component that is operating in a different environment, which is harsher, one would then anticipate that these failures occur earlier. And if it is in an area which works in an environment which is much more benign, you would anticipate these failures or these damages would accumulate much slower. The future or new emphasis has become, as I said earlier, would be on thermodynamic, because these failure mechanisms all dissipate energy. And we know that dissipation of energy corresponds to entropy generation according to the second law of thermodynamics. So therefore, the idea is for every failure mechanism, find the entropy which is generated, and find how much, instead of the capacity of the endurance, find an entropy to failure, or endurance, how much endurance to entropy each item would have. Therefore, in this case, entropy would increase over time until it reaches the endurance to the entropy, and a failure occurs. Many tests recently have shown that actually, regardless of how components, they go through different paths or loading, once they reach this level of entropy, they fail, regardless of how they fail. The other good thing about the entropy is that entropy does measure essentially the entirety of the damage, not just the markers of the damage, and that alleviates the problems which I noted earlier. So in this case, entropy can be modeled multiple competing degradations in the system. Entropy is independent of the path to failure, and failure occurs once entropy accumulated to a given level. Entropy accounts for complex and synergistic effects among different components, different interacting degradation processes. So for instance, if you have corrosion and fatigue together and they could affect each other, in other words, corrosion could promote fatigue to go faster or vice versa, these kinds of methods, entropy can actually easily account for those kinds of synergies, whereas the probabilistic physics of failure still could model them, but actually with more difficulty. And finally, entropy is scale independent, so you could apply it to micro level units and as well as macro unit. So this has been the reasons that we are going to this. So in conclusion, reliability engineering has relied on historical evidences and still does, but sometimes it creates inaccurate perspective of the true reliability, especially if the data are not relevant to the reliability model that is derived from those data. Physics of failure has come to alleviate that. It allows us to do simulation, but also it's empirical and it's somewhat judgmental at certain aspects, but it does much better than the data, purely data-driven, and it could actually then capture specific stresses or conditions that the item is supposed to work in, and therefore narrows the errors that you could have. Finally, the entropic damage is the new wave of development in reliability engineering, where the damage degradation is developed based on the fundamentals or the second law of thermodynamics, where the damage and aging assessment in reliability engineering can be used. PHM applications have become very much prevalent these days, and they have become a leading approach in improving reliability during normal operation to improve maintenance, replacement, and repair of different items. And thank you for your attention.